Here's an introduction to space-based telescopes to accompany Chapter 6 of the textbook Astronomy from Open Stax. So, why don't we have every telescope on the ground? We covered this in the ground-based telescopes lecture. Only a portion of the electromagnetic spectrum can actually make it through the atmosphere to the surface of the Earth. So, very long radio waves, right? These are blocked by the ionosphere. Much of the infrared is actually absorbed by water in the atmosphere. The visible and some of the UV can punch through, and then the X-rays, these are just absorbed by relatively thin layers of material, so just by any kind of gas. So if you want to observe X-rays and gamma rays, unless the gamma rays are very high energy, then you need to have something out in space. And that's true for a lot of the UV and the infrared as well. And even there's still advantages for optical telescopes, like we talked about in the ground-based telescopes lecture, that sometimes you even want to put an optical in space because there are some advantages there. But of course, the point here is that you just need space-based telescopes to observe a large range of the electromagnetic spectrum. So that's why we have to put some in space. Why don't we put every telescope in space? Why not? Well, I mean, there are some obvious reasons here, but let me just spell them out. So money is probably the biggest one. So here's just some comparisons. The purple ovals, these are ground-based telescopes, an existing one and a future planned one. These red rectangles here, these are space-based ones, so a current and a future planned. And you can see that you're talking about much more money for a much smaller device. So billions of dollars compared to tens of millions for a smaller device. And even this really huge sort of next generation optical telescope, 30-meter telescope, this is still half the price of Hubble, which is a completely tiny telescope, relatively speaking. Okay, so money's probably the biggest reason. Even if it weren't for money, there's still some other reasons you wouldn't put everything in space. There's risk associated with it. So rockets do fail, and more than one astronomical instrument has gone up in flames in a sort of launch type disaster, so there's some risk. And then there's also a lot of inconvenience to having a telescope in space. It may be difficult or usually impossible to service, depending on where this telescope exists. And I mean, a famous example of one that was luckily difficult and not impossible was the Hubble Space Telescope. So it wound up costing around $5 billion. When Hubble was launched into space and first used, this was an image seen from a star that's supposed to be one point. Instead, you had this horrible situation, and a galaxy looked like this. And the issue is there was a minor flaw in manufacturing the mirrors for the telescope, and that needed to be corrected. So corrective optics were made, because you couldn't replace the mirrors, it just wasn't feasible. Corrective optics were made, flown up into space, and the astronauts had to install these basically glasses on the telescope, and finally you could get nice images. So it's pretty inconvenient. There's really no room for error, or very little room for error, and mistakes can be very costly. So what are some examples of some X-ray telescopes? Just one of them, for example, is Chandra. So this is a satellite that orbits the Earth. The orbit is highly elliptical, so Chandra spends most of its time very far from the Earth, and this is a beautiful GIF animation of showing Chandra's orbit, this neat little path that it takes. But it's very far from the Earth, and the reason that that's done that way is for the elliptical part of the orbit where it's far from the Earth, Chandra is outside Earth's radiation belts. So we'll talk about this much later. The Earth has these regions where the Earth's magnetic field interacts with the solar wind, the charged particles emanating from the sun, and where they interact, these charged particles basically get trapped in a region around the Earth. And the annoying thing is these charged particles then will hit your X-ray detector on your telescope. You can deal with that, but ideally you'd like to avoid it. And so that's what Chandra does, is it just mostly orbits very far away from those and avoids that background. Another example is one that I've used in my own research as a consumer of the data. I'm not an observational astronomer. Is called MAXI, and this is on board the International Space Station. So the convenience of being on the space station is that it is a serviceable instrument. So it, astronauts can repair it because it's right there on the International Space Station. One downside is though you do get solar radiation on it. So that's a background that just has to be dealt with. This is an object that winds up scanning the sky. So another big difference is that the Chandra orbits are very long, and you spend a lot of time away from the Earth. Because MAXI's on the space station, it's every 90 minutes. It's doing laps. So the downside is that you're frequently blocked by the Earth. The upside is that you scan the whole sky with a relatively high frequency. So that's kind of nice. So how do these telescopes work? Mostly I'm going to say X-ray telescopes, but most gamma ray telescopes work kind of the same way, unless you're talking about very high energy gamma rays. So the issue is we can't use the same system as an optical telescope where your light, and hits a parabolic mirror and then bounces back to some light collector, because the problem is that high energy photons don't follow that path really. So your scattering angle does depend on the energy, and for the most part, high energy photons are scattered close to the same direction that they entered. So that scheme wouldn't really work where your light comes in and bounces back, because the scattering is mostly going to be very small angles. So instead, these things called grazing mirrors are used, and it's not really a traditional mirror. These are heavy metals, so it's a more exotic type of mirror that can take higher energy radiation, and they'll be, as the name suggests, the light will graze off of these and reflect at small angles, and you put a handful of them together so you can kind of gradually reflect into the point that you want, to the actual X-ray detector within the X-ray telescope. So for imaging, the detector is often a charge coupled device, a CCD, that we talked about in the ground-based telescope lecture. So that's how you can collect an image. So you have many pixels in the X-rays. Deposit their energy essentially into each pixel that gets converted to electrons, and you can get an image. The other common type of X-ray detector is a counter. So you're really just trying to count the X-rays. Particularly this is useful for faint objects where you don't have a lot of photons to work with. And often a proportional counter or a scintillator will be used. So the proportional counter, we use these for actually nuclear physics experiments or measurements in the lab on campus that we have. So what this basically is it's a gas-filled box or tube. And so this region here is just kind of gas-filled, some box of gas or a tube. There's a high voltage wire inside that box or gas, and when a photon, an X-ray, comes through, it will wind up ionizing the gas, and electrons freed from the atoms in the gas are then drifted towards this wire because the wire is at a high positive voltage and the electrons are negative. And so you can collect those electrons, and you know that an X-ray went through, and so you just count. Another type of counting detector is the scintillator. So here what happens is your photon, it winds up interacting with an atom or a molecule within some scintillator material, and that excites it. The energy is deposited in that molecule, for instance, and then that molecule will de-excite, and it will wind up emitting photons at a lower energy. And these are easier to deal with, and these are converted to electrons using the photoelectric effect that we talked about in the ground-based telescope lecture. Now, interestingly, sometimes you don't actually need to go out in space for some of these observations, and a great example is the infrared. So, while X-ray radiation is absorbed by a small amount of gas, infrared mostly interacts with the moisture in the atmosphere, and so that's why it's it's difficult to observe it from the ground. But what you can do is consider the fact that the moisture in the atmosphere depends on the altitude. So what's shown here in this plot, the horizontal axis is the concentration of water in the air. So at sea level where you're at, the air is about 1% water. But as you go to higher altitudes, this decreases, and it decreases quite a bit. And so there's less water for your infrared photons to interact with, to get absorbed by. And so what you can do is instead fly a telescope on a plane at a high altitude. So this is the SOFIA telescope. It flies at a pretty high altitude, but nonetheless something a plane can do. And this is just a modified plane, and that's literally a telescope stuck in the side. And you open up the hatch and observe as you fly. And this is, obviously extremely expensive because it's still very complicated, but it's a lot cheaper than sending a satellite into space, and it can be regularly serviced, right? So that's nice. Of course, there are challenges because you're flying on a jet, so that adds some challenges to the observations. But nonetheless, this is one way that infrared astronomy is done, incredibly enough. And that is it for this introduction to space-based telescopes for Astronomy 1000.